This map shows the temperature fluctuations of the cosmic microwave background. This thermal snapshot serves as our primary observational baseline for mapping the early universe. To figure out what the universe is actually made of on a macroscopic scale, cosmologists extract the total energy and matter partitions by inferring parameters directly from this observational data. The Planck 2018 Base Lambda CDM model breaks the observable universe down into three highly specific fractions. Roughly 68.9% goes to the cosmological constant, 26.1% to cold dark matter, and the remaining 4.9% to normal baryonic matter. The standard assumption in cosmology is that these percentages are purely empirical. They are treated as numbers fitted to match the observational data, rather than laws mandated by a mathematical structure. That leaves an open question. We need to know whether these specific cosmological fractions are numerical accidents of our current epoch, or if they share a rigid underlying geometric origin. Independent researcher Nadav Bashan has proposed a theoretical framework that derives the cosmic baryon fraction from pure geometry. The core thesis argues that if we treat the cosmological horizon as a thermodynamic boundary, that physical limit directly dictates these exact density parameters. Instead of taking the data and fitting parameters to it, this framework works backward. It peels away the measured numbers to reveal mathematical constants that generate the observed fractions. This is a strictly macroscopic approach. It requires zero microscopic models of particle physics and introduces no new dark matter interactions to explain the ratios. If this mathematical construction holds, the lambda CDM parameters stop being independently fitted variables. They become closed algebraic consequences of spacetime geometry. The mathematical buildup starts with the geometry of the Hubble volume. We define the radius of this horizon, r sub h, as the speed of light divided by the Hubble constant. From there, we introduce a starting geometric axiom linking the cosmological constant, lambda, to the area of this horizon. Lambda times the horizon radius squared equals pi cubed over 15. We then take the standard cosmological definition for the universe's present-day dark energy density parameter, omega sub lambda 0. By substituting the definition of the horizon radius into that standard dark energy equation, the algebraic terms collapse. The math resolves perfectly to an exact geometric value. The dark energy density fraction is equal to pi cubed divided by 45. Run the numbers and pi cubed over 45 evaluates to approximately 0.68903. Without relying on empirical curve fitting, the universe's dark energy density is mathematically locked by the thermodynamics and surface area of the Hubble volume. Cosmology operates on the widely accepted observational condition of spatial flatness, meaning omega sub k equals 0. Under spatial flatness, the total matter fraction and the dark energy fraction must perfectly complement each other to equal exactly 1. To find the total matter fraction, we calculate the complement by subtracting the derived dark energy fraction from 1. That subtraction leaves us with a total matter fraction of approximately 0.31097. Fixing the spatial geometry automatically fixes the total macroscopic matter sector in a closed form. This happens before any split into baryonic and dark components occurs. The physicists who built the foundation of modern gravitational physics were the first to associate horizon surfaces with temperature and entropy. Today, assigning thermodynamic properties to horizon surfaces is a thoroughly established standard in theoretical physics. In this geometric framework, the cosmological horizon functions specifically as the ultimate thermodynamic boundary for any observer inside the universe. For an observer positioned exactly at the center, this spherical boundary constitutes the absolute limits of causal interaction. Any thermodynamic interaction between that distant boundary and the interior observer must rely strictly on geometric lines of sight. Looking at the spherical boundary of the Hubble volume from the outside, the total surface area covers a full 4 pi steradians. But an interior observer is subject to a one-sided radiative projection originating from the boundary itself. Because they cannot see the outside of the sphere, the operative angular domain of boundary crossing is solely this one-sided half-space. That restricted interior-facing angular measure subtends exactly 2 pi steradians. Bashan identifies the baryonic sector, normal matter, as the radiatively coupled share of the previously fixed total matter sector. To calculate it, we substitute the exact geometric expression for total matter and divide by that 2π projection factor. The math results to a theoretical fraction of approximately 0.04949. The specific percentage of normal baryonic matter is derived entirely from the observer's 2π restricted view of the thermodynamic boundary. With the theoretical geometry completed, we can test this derivation directly against the empirical data. This diagram shows the side-by-side comparison. We have the Planck observed value for baryon density against the pure geometric derivation. The derivation matches the measured observation, sitting well within the margins of error with a deviation of just 0.22 sigma. Because the total matter and baryonic matter fractions are now geometrically fixed, the remaining non-baryonic dark matter component is found through simple subtraction. Subtracting the calculated baryonic fraction from the total matter sector yields a closed form for dark matter, approximately 0.26148. This framework correctly predicts both macroscopic matter partitions, strictly within the bounds of modern observational cosmology. The math also yields a secondary consistency check, the sector ratio of dark matter to baryonic matter, which calculates out to 2π-1, or roughly 5.28. That pure geometric ratio sits close to the observed Planck ratio of approximately 5.36. Because the math produces exact values, the model outlines clear conditions for its own falsifiability. The entire construction fails if future, more precise measurements of the total matter or baryon fractions confidently break the current 0.22 sigma alignment. This calculation resolves the matter partition macroscopically, entirely sidestepping microscopic particle models of dark matter. By recognizing the cosmological horizon as a thermodynamic boundary, the cosmic baryon fraction ceases to be an independent fitted parameter. It becomes an exact geometric property of spacetime.